Yo, what's up, guys? Welcome back to another video. And you might be wondering, what the hell happened to my original setup? We are in a conspicuous website, which I will not name because I don't know if I could say their name. It's made by Microsoft, though. But anyway, today we're going to be talking about partial derivatives. And so you might be wondering what that is in terms of, derivative. Because you see the word derivative and you expect to see f prime of x, f double prime of x. But, you may hear the word partial derivative and you might be a little bit confused as to what that is. Do not worry. Partial derivatives just mean that in the multivariable function, so let's say you had the multivariable function of f with respect to x and y equal to x squared plus y squared. Let's say you wanted to find the partial derivative of this multivariable function. Since in a 3D coordinate space, you can't really do the derivative at exactly one point. You have to find the partial derivative in order to find what's happening on that specific plane or octant or whatever you're trying to find. Since it's not 2D anymore, you have to do partial derivatives in order to find it. I also find it pretty interesting because calculus stems much more than what the 2D is, 2D, you have your integrals, your usual derivatives, but then you go to 3D and it's like, whoa, we're just throwing all the laws of math away. So here's what partial derivatives are. There's two notations for it that I like to use. I don't know if anyone else teaches you differently. They might teach you differently. But I like to use mostly what represents the function. So in this case, f of x and y. So the partial derivative of f of x is notated as f with a little x as a subset. Subset? I don't know what it's called. And you can also have this notation where it's weird and I don't like it. Yeah, we don't like this. I don't like that. It's hard to draw. Essentially, what you do is for a partial derivative, when you're taking the derivative with respect to that variable, you leave every other variable as a constant, essentially. So essentially, when we take the derivative with respect to x, y is a constant in this case. So imagine you had the function f of x is equal to x squared plus 5. When you take f prime of x, you'll get 2x, right? Same thing here. We treat every other variable that's not that variable that we're trying to find the derivative of as a constant. So we treat it like a number. It's not really a number though. It works though, promise. And I'll show you later on. And it gets confusing when you get into, a bunch of things. So let's say you had let's say you had a multivariable function of x squared y plus y squared x squared, right? Let's take the partial derivative of it. F partial derivative of x is 2x. Remember, we have to treat every other variable that's not x as a constant. In this case, you'll keep x squared y. You only keep y as a constant. So your partial derivative for this first part is 2xy plus 2y squared x. Pretty simple. And then when you're taking the derivative with respect to y for the partial derivative, you're going to see that x squared is left as a constant. Since y, when you take the derivative, it's just 1. And then you're going to get plus 2y x squared. It seems pretty weird at first, but I promise it makes sense. Later on, you can start making crazy equations with the z variable as well. It's pretty interesting, really. I could do something like this and then, just find everything that I need to find for it. So we have the multivariable function of f of x, y, and z this time. And the function is xy times e to the 4th xyz power. Promise is easier. Ooh, college kids outside. They're gonna hear me talk. We're gonna be like, shut your ass up. When we take the derivative with respect to x, we're going to have to do chain rule and that one product rule. Let's do it. We have xy times e to the 4xyz. And remember your rule for e to the power of x variables. You have to take the derivative of this thing. And since the derivative of 4xyz, we're just keeping 4yz constant. It's just gonna be 4yz plus, because product rule, 4xyz times y. And that's your partial derivative for x. It gets very long, promise it gets easier. We're gonna have to do the same thing for f of y. So we have just xy times e 4xyz. And remember, we're gonna keep everything constant except for y. So it's gonna be 4xz plus e 4xyz times x. Reason why we do x this time instead of y is because, again, it's being kept as a constant. So when you do product rule, you're only taking the derivative of y. Then we do the same thing for f of z. For f of z is actually pretty much easier. Since everything else is being kept constant, you only have to take the derivative of the e function. So you get xy e 4xyz times the derivative of this with respect to z, which is 4xy. Yeah, it's pretty complicated. I can't lie. It's pretty complicated. It's pretty complicated. So now let's say you want to put some points to it. Let's say you have the multivariable function of x and y, and you have, like, I don't know, 2, 1. Why not? I don't know what you're doing. I don't really care. Let's just say you had that. Then you had, like, what? Y squared x squared plus y to the third x to the third. I don't know. Just make some crazy function up. We're going to solve it anyway. And you want to find the partial derivative at that point. I don't even remember, bro. Like, I don't even remember. Like, I don't even, like, I'm actually so exhausted right now. But let's find these partial derivatives first. Because just like in 2D calculus, you have to find the derivative first and plug in a point and see what that point is at that point. Does that make sense? I don't even know. I'm half tired. We're taking the derivative with respect to x, so we keep everything constant except for x. 2xy squared plus 3y to the cubed, I'm so sorry, x squared. F of y is equal to 2y x squared plus 3y squared x to the cubed. So now we're going to plug it in. Since we have 2 points and the y's in both ones, we're going to have to plug it in for each of them. So we're going to have to plug in f of x, partial derivative of x with respect to 2, 1, since those are the points. And we're literally just going to plug everything in, bro. Like, there's not much to it, really. Can I even do simple math? Oh, shit. You're going to see if I can do simple math. We have 4 times 1, which is 4. Plus 3, 1 to the cube, this is 3. Times 4, because 2 squared is 4, which is 12. So the partial derivative with respect to x of 2, 1 is equal to 16. And then when you take the same one for f of y, oh my god, not f of y, for a partial derivative with respect to y, you're going to do everything the same. Just going to plug in the same values. Or we're going to get a big number. You're going to have 2 times 1, which is 2. 2 squared is 4. So this will be 8. Plus 3 times 1 squared, which is 3. Times 2 to the cubed is 8. So it's going to be 8 plus 24, which is equal to 32. And so evaluate your partial derivative with respect to y. when you plug in the 0.21. Man, I could really do something right now, bro. It'd be so crazy. I'm actually so exhausted. Like, it's 3 in the morning. You can tell. One more example. We're gonna change the color because I can do that. Look at me, I can change the color. Oh my god. Oh my god. Let's make some random function. Oh my god. Let's do e to the 10xyz. Why not? I don't care. And we're gonna make the points 1, 2, and 3. Let's take the partial derivative with respect to x, with respect to y, and with respect to z. This is pretty easy because I didn't add anything up front, so we don't have to do product rule. Could always leave this as a challenge, but we're mathematicians. We're not arithmeticians. That's the difference. When we take the derivative with respect to x for the partial derivative, we get e 10xyz times 10yz. Because again, you have to keep everything constant except for the x in terms of partial derivatives. You do the same thing for f of y. What's the xz? Yeah. And same thing for f of z. Oh my god. Partial derivative of f of z. Is that xy? Yeah, I think so. I don't even know myself. And then from here, you have to plug in the points for 1, 2, and 3 for each one for x, y, and z. Also, if you haven't noticed, this stands for x, this stands for y, and this stands for z. Since usually it's x and y, when you go to multivariables x, y, and z. Fun fact. So now we take the partial derivative of x, plug in these points for x, y, and z. And you're going to get e to the 10. Oh, I didn't think about this one. 1 times 2 times 3 times 10 times what? 2, 3. Then we're going to do the same for partial derivative of y. Really? If you wanted to, you could just plug everything in and you will know. Like, you don't have to do, just multiply everything. You know that e to the 10xyz is always going to stay the same. So what you really could do is, for me, such a little shortcut, I just like to plug it in, right? You meant like 60. Yeah, it's just e to the 60 times 10 xz, which is what, 1 and 3. Then partial derivative of z, which is equal to e60 times 10 xy, which is 1, and then y, which is 2. So the partial derivative with respect to x in terms of the points 1, 2, 3 is going to be e to the 60 times 60. Wait, is that right? Wait, what? Yeah, e to the 60 times 30. Okay. And then f of z is going to be e60 times 20. Fun fact, that actually goes down by 30. But yeah, guys, that's how you plug in that's how you do partial derivatives. It's really, really simple. Concept is really, really simple. It only gets harder when you have to do like implicit differentiation. Then you have chain rule. This isn't chain rule, by the way. Like, this is like baby chain rule. Like, it's gonna get so much worse. And like, I'm actually so exhausted. I wanna cry. I'm having a breakdown. But that's been partial derivatives though. If you have any questions, because I might have been confusing. Like, I'm so sorry. I'm that tired. Leave a like, subscribe, please. I'm a broke college student. I need all the help that you can get. That I can get. Please help me, please. This has been partial derivatives, though. I'll see you on the next one.